Hello, welcome. My name is Andrew Lamb. I'm going to now present column storage for the AIEra, which is a talk I'm going to give at TU Darmstadt's joint database seminar series with HPI tomorrow. This is joint work with Julien Le Dem, and I'm going to try to explain, basically, at the high level, why we've seen so many new Parquet proposed replacements. As I mentioned, my name is Andrew Lamb. I'm on the PMC of a variety of open source projects, and I'm including Parquet, AIEra, and DataFusion. So of course you should understand that what I say should be taken with a grain of salt. Right? I have definitely a perspective on Parquet and how valuable it is to the open source ecosystem. But I'm a staff engineer at Influx, and I've been working on these technologies for quite a while. My goal today is to try to answer the question why there's 8 or more new proposed file formats in the last 2 years. And in order to do that, I'm going to try to explain where the current columnar file storage formats came from, what was driving the ecosystem at that point, what's currently changed with the ecosystem, and then I'm going to try to describe what I think are possible futures or ways to, evolve with that workload. Of course, the thesis is AI is the reason, as is everything these days, but I'm going to try to dig into that reason why. So we have to start with where we came from. So where did we come from? What that means is you got to understand sort of some of the history to understand where Parquet came from and where we are right now. I'm well aware databases predate 2000, but this is about when I joined the computer science profession. And so this is about when my historical perspective starts. So you can see we were going through various ecosystem transitions from mini computers to servers. In the 2010s, around when Parquet was created, we were in the process of switching to clusters of networked machines, which I think drove a lot of the design decision about Parquet, which I'll talk about. We've seen the last probably 10 years a switch to the cloud, which basically is VMs and other people's servers, and a variety of other sort of hardware changes, additional parallelism, and then we're in sort of the next transition, I think now, maybe people call it the AI era. And so I think basically we're going to see significant something happen here, right? Is this going to be Parquet? Is it going to be some new file format? I don't honestly know, but I hope this talk helps sort of frame the discussion. To remind you, back when I was in college, it makes me feel really old. These Sun Ultras were like the hot thing, so we'd go to the computer lab, and those were very, very cool. Like there was still a physical lab you went to. Not everyone had a laptop. But we're in the middle of transition from like one relatively powerful machine that basically databases and stuff ran on to clusters of like inexpensive machines. Now, in those days, inexpensive still meant $10,000 a piece, and they weighed 50 pounds. This is a stack of DL380s. I still remember getting some of these at Vertica and physically helping them physically unload off the truck. They're very heavy, and then put them in racks and power them up. And we had special, and it took us, I think, about 6 months to provision them. But that was like a world-changing thing because you just buy more and stick them in rather than have to scale up, right? This is the state of the art at the time. That was like $500,000. These were $10,000 a piece, so significantly less expensive. And so in the context of that, where there are lots of individual machines being now connected via a network, figuring out how to do distributed computation became a thing. So that was a large part of where MapReduce and Hadoop fit in. I think at this point there was a significant gap between I/O and CPU. As you might recall, your database textbooks from back in the day basically ignored the CPU cost entirely because all of the algorithms were I/O dominated. I think you can also kind of see a hint that the I/O and networking were much less prevalent than CPU cost because at that point Java was a significant technology used in these analytic processing systems, and I think that's especially driven by the CPU was not typically the dominant. That was not the problem. We had plenty of CPU, network bandwidth, and disk storage were typically it. And also in the context of this, there were interesting academic works talking about how if you stored data in columns, you would get significantly better I/O and throughput. So this is sort of like where we were, and it's in that context that Parquet comes along. It's basically designed for analytic reporting. So that means taking large amounts of data. At this point, the data was starting to become largely machine generated, like call detail records was an example, and you're basically crunching those down into summaries for humans to consume either via dashboards or reports or that kind of thing. And so those systems were largely optimized for throughputs. That'll show up in the talk in a few more minutes. And also there was distributed systems was a big thing. We didn't really know how to build distributed databases at that point. And so figuring out how to do distributed computation when the data actually lived elsewhere and you had to transfer it over a relatively slow network was important. right? And I think Julien actually says sort of one of the reasons he started Parquet was to try to make it more like Vertica, which was taking advantage of some of these column store advances in the academic field. So typically, for these type of analytic file formats, the trade-offs are between storage, CPU, and transferring the data between the storage and the CPU, so either network or locally. And back when Parquet was done, as I've mentioned, the network was much less, had much less throughput. And you can see a bunch of the trade-offs in Parquet that were made were really designed for that. So there were certain trade-offs that are clearly better for everything, like storing a binary format with self-describing schema, putting it in columns. That was all good for both storage, network, and CPU. Splitting the whole file not into individual columns, but it's actually stored in like sort of strips of columns that are called row groups or stripes. The academic term for that was Apache encoding. You can also start seeing, though, there was a lot of emphasis in Parquet placed on general purpose compression and encoding. And this is great for storage. It reduces the file size. It's great for network. You have fewer bytes to transfer over the network. It's not great for CPU usage because now you've got to do decoding and decompression. However, given the abundance of general purpose CPU at the time relative to other things, I think that was the right trade-off. And also, there's an interesting choice in Parquet to add sort of metadata at the footer that lets you then interpret the rest of the file. That's actually not great for latency in the sense that you have to now make a request to get the metadata, process the metadata, then go make the requests for the pages of interest. That improves the network throughput, but it does not really increase. In fact, increases the latency. And I've purposely highlighted these things in pink because this is very much the places that I think Parquet has challenges these days. However, challenges aside, Parquet is actually doing pretty good. 15 years later, I think everyone pretty much acknowledges that it's the dominant open source analytics file format. There's a bunch of existing implementations. This is from the Parquet website. It basically shows that the feature parity across implementations is actually quite good, right? So even though there is a perception perhaps that it's really hard to add new things to Parquet, I think when you look at it realistically, there actually has been quite significant adoption. And I think this is part of why it's been driving across the ecosystem, why it's become the dominant format. All right. Oh yeah, by the way, of course, actually getting everyone to agree is a whole separate talk. Maybe I'll give that some other day, but today is really about the technology. So that's what Parquet is. And so the question is, where are we going and what's happening? So I think the first thing to just illustrate the fact that there is a problem happening or a shift happening within the last 2 years, Andy Pavlo identified at least 8 new file formats. This probably undercounts some of them because we didn't know all the potential options. But the idea here is that something's driving this, right? Like, why in the world are there 5 new file formats being proposed, both from industry and academia? And I believe there's at least 3 major driving principles which we'll delve into, which is, of course, something related to AI, which is the access patterns of the AI applications. Again, I'll talk about that in much more detail in a second. But also the unbundling of the data ecosystem, I think, helps drive it, as does, of course, evolving computer hardware. And I think those pressures are really pressuring the existing features of Parquet. So what are new AI access patterns? Of course, AI is the hot topic now, but I think after studying some more of how the AI actually is trying to access data, I think it makes much more sense now to me. And so I wanted to try to explain that to you if you're interested. So the first thing is we are seeing the arising of feature stores. So when I was back at Vertica, I keep telling people, if a customer came to us with like 20,000 columns, we'd basically say, like, not only could the software not handle it, but we tell them you're doing something wrong, right? There's something wrong with your schema. You need to change your schema in your application or something. There's no actual use case for having 20,000 columns. And I think that's actually actively changing. But so what people would do typically is you'd add more data at the bottom of your table. Okay, you add more rows. So we had systems that were designed for very, very large numbers of rows, relatively small numbers of columns. Like about 1,000 columns is where I think most databases these days, or most relational databases, are pretty happy. And if they do support adding columns over time, but typically you backfill them with very simple things, either null, possibly some constant value, possibly some simple calculation from the pre-existing rows. And because they're pretty simple, if you try to backfill, you can actually sometimes just fill them in at query time. You don't actually have to go back and rewrite the data or add new actual physical columns. I think what we've seen now with these feature stores, however, is when people are building machine learning applications or AI applications or whatever, you have your data set, you have features that you've either extracted out of the data or pre-computed vector embeddings or something. We'll talk more about them. And so not only is the table growing down, right, more and more rows, more observations, but it's also growing wide, and they're not just getting added, sparse columns or constant columns. They're like real new, seriously dense columns. And the access pattern is still the same, where you're only fetching a small number of these columns, but the actual data size is growing to the horizontally now as well. And so I think classic systems, including Parquet, where there's some limit on the number of columns before stuff starts getting unwieldy, that I think is starting to become more of a problem. By the way, I wanted to say thank you so much to Weston Pace and the LansDB blog, which is where I got these pictures from, and I think the writing there really helped clarify this for me. So the point is, having a file with 100,000 columns, you can no longer just say you're doing something wrong to the person who wants that. There's legitimate use cases for it, specifically feature stores. Now you could argue maybe some of this is better handled at a higher level with table formats, but actually even this use case of slapping new columns onto an existing file with like new data, not just backfilled with constants, is not really well supported even by Iceberg today. The other new AI access pattern that, again, is all the rage is RAG retrieval. There might be other better words for this, but at the high level, here's, from an IBM architecture guide that kind of tells you this is a standard way of architecting these applications. Let's not worry about the top, but this, if you look at the bottom, you're basically interacting with an AI app. The query comes in, whatever the query might be, interacts with the app. The first thing the app does is it has to search the vector database for relevant information. I'll talk about that in a second. And then that information is sent on to an LLM, which processes and returns the response. Why I'm highlighted this interaction with the vector database is because this now is on the critical path to returning results to the user. And so analytic systems previously, right, you would pre-compute a report, and so fetching the actual results was not on the critical path for some sort of business case. But now it is, and I think that really drives people's interest in low latency queries. So the fact that the faster this thing can fetch the data in the individual rows back to feed to the LLM, the faster you're going to get the results back. So the fact that this type of application is growing in interest, right? And this is a non-trivial query, right? This is doing some serious computation. It's not just like a transaction system. So that's driving additional pressure on low latency queries specifically. This is a text file that basically says what I just, or the text slide that says what I just said. If you're interested, I really like the fact that the SpiralDB guys like Will Manning, if you read their funding announcement, they're the guys behind Vortex, by the way. They changed this as, instead of the data being fed to humans, right, we can only absorb data so fast, it's instead being fed to machines. And because it's being fed to, aka LLM models specifically, because it's being fed to machines, the actual, they can absorb the information much more quickly and a lot more of it. So that's why these sort of extract and read a lot of single row workflows is becoming more important. And the final AI access pattern is this vector search. I think that's also driving some of the common things we hear about Parquet. This is, again, a picture out of a LansDB blog. It's not, the actual blog is not really about vector databases, but I think the picture serves enough that I can use it to sort of describe what I see as a difference in the pattern. So in this case, what this is showing is sort of what you would store in a database, right? So maybe you have some images, but what you'll do to those images is you'll extract features, in this case, whatever these shapes, and then you'll compute some sort of embedding on them to figure out maybe what's in the shape. Somehow that's encoded in this effectively big matrix or a vector. And when a query comes in looking for a dog, you translate that query into an embedding, so one of these binary vector things, and then the actual embeddings have been stored in the database, and so the query itself actually has filters on this column. So unlike in the past, where if you had binary data that you were storing in a database, right, we've had you'd store it in a blob or a CLOB, which Oracle's had for probably close to 50 years, which is basically a pointer in the database that points to the actual file content somewhere else. That works great if your use case is find the relevant record based off traditional sort of attributes, right? Traditional relational attributes, and then just look up fetch the final document as the final pass. What's different about vector data is the actual query involves these binary columns. So the binary columns are part of the query filter. And so I think that means that you can't just sort of store these things externally and then fetch them during query after you've run the query, because they're an integral part of the query. And so this is driving a bunch of concern and basically how do you process these large sort of binary things as part of an analytic column file format like Parquet. And specifically, it shows up like Parquet is not great with strings or binary things. And again, this is me trying to make some slides so that if you're watching this after the fact, you want to refer to them. This says basically the same thing, but the key idea is that those blobs, right, the binary things are actually part of the queries now, and that's means they're important to store efficiently in the file format. Something else that I think is really driving pressure to evolve the open source file formats, Parquet specifically, is this analytics ecosystem unbundling trend we've seen in the last maybe 3 or 4 years now. The traditional, even like a disaggregated database like Snowflake, you would end up with a vertically integrated software stack. So in this case, you'd have your catalog, your query engine, caching layers, all that sort of stuff was all engineered to work well together, in addition to and then a specialized file format. And so what this meant is, this classic example is this, or Redshift, Snowflake, Datadog, Husky has a similar thing where they've got a specialized file format along with a custom engine and custom catalog. Now, I think in this case, if you have a new application like a RAG or vector search or something, and you control the whole thing end to end, it's fine. You'll just update the file format to support whatever query patterns you want, and you're good to go. And it's not really a problem. However, I think the trend over the last few years is, instead of building these big vertically integrated software stacks, instead you build software out of components. And in this case, what you do is typically you'd assemble the components that you need for your particular workload or application, and you build them out of reusable components, and they all share traditionally, like the classic thing is they store data on object stores using open file formats. And the reason that they're stored openly is so that you can basically spin up these customized analytic applications. You don't have to then also pay to transfer the data to a new format and then also keep it synced, right? You have one source of the data with this constellation of new things. And so basically, because of this pattern, because it's easier now to build new analytic systems, as new use cases come along, specifically all these AI use cases, there's a lot more pressure on this common file format to support those new use cases more efficiently. Right, so I think that's another thing has also been arriving or been driving. And there's a whole bunch of example systems like this. A lot of these are DataFusion users, but DataFusion is certainly not the only part of this ecosystem unbundling story. Yeah, and I should also point out, it's not just sort of products that people have built. There's also often internal custom data systems, right? They'll have a specialized data, either ETL pipeline or query pipeline for some particular business-specific use case, and those will get, they want to use these custom file formats in order to drive this architecture, but that also means if the file formats don't support the use case, great, there's a lot of pressure now to evolve those file formats. And of course, the last thing, which I don't need to tell anyone, is that computing hardware is evolving. So in this case, there's, I think, 2 major trends we've seen a lot recently that'll, I think, put pressure on Parquet to evolve. The first is obviously more parallelism. I still remember, like, when we were working at Vertica, it was like a huge deal to have a laptop that had 2 cores. Like that was a real hot thing. Like those were expensive laptops. These days, I went to look at the most entry-level laptop I could find right after 2 or 3 minutes of Googling. All of them have 4 cores. You have to work pretty hard. Like you can't really find anything with less than 4 cores these days. Even the cheapest Chromebook I could find had 2 cores. Cell phones have like 4 or 8 now. So the point is, there's massive parallel hardware out there, and of course, on the high end, the new NVIDIA chips have some ridiculous number of cores, like 20,000. I think another thing that we're seeing a lot that I don't really know how it's going to play out yet is that instead of just sort of getting more and more of cores that are the same, we're actually getting more cores that are like specialized for different applications. So obviously GPUs are an obvious example, right? They're probably the biggest example. But I think even locally on my laptop, right, I think it has 16 cores, but they're not all the same. I think it has like 12 power cores, maybe it's 4 efficiency cores, something like that. And you can also see a lot of heterogeneity across the instruction sets. Like the different chipsets have, not only do they have different instructions for the different SIMD architectures, they also actually have different like width SIMD lanes. So the point is there's a whole bunch of non-uniform hardware coming out, and so I think that's also driving the need to sort of have the file formats better support these in the new hardware. And I'll explain more about what they're talking about in a second. So now I'm going to switch from trying to explain what I think is the current state of the art, maybe, to now articulating more about what we're headed. So the first thing I'm going to do is summarize what the people's complaints that I've heard about Parquet. So not just I, but other people, and these are basically typically what gets cited for why people need a new file format. And I think these are directly driven by the use cases I just described, right? So a big thing people talk about sometimes is that Parquet is slow if you have tens of thousands of columns, because it has slow metadata, or you'll hear that as slow metadata parsing because of Apache Thrift, which again we'll talk about a little bit in a bit. You will also hear a lot about how Parquet has high latency reads, or alternatively slow random access. So if you're just doing point lookups, for example, you'll hear that Parquet is not good at that, or you'll hear that it's very high latency to read, and that's typically because it has this general purpose compression stuff, which I'll talk about in depth later. You'll also often hear that Parquet is not great, or it's overly memory intensive when you're fetching large strings or binary. Again, I think that's directly driven by people wanting to store those vector embeddings directly in the Parquet files themselves. And when they do that, I'm not saying the format's actually not good for this, but people's perception is that it's very memory intensive for columns like that. And I think another very common gripe is you can't really take advantage of all this new hardware, neither the parallelism like across cores, or really take advantage of these SIMD or highly parallel GPUs. People will also point out that people also like to complain that there's multiple distinct implementations and that that's a problem. I actually personally think it's a strength, but I realize that's not a universally held opinion. Right? That it's basically, if you have to get a bunch of people to agree on a direction ahead, that takes longer than if you just have a single implementation and go. But it has a bunch of other benefits, like longevity, for example. But anyway, that's another talk, as I described. So let's talk about metadata. In this case, today, I'm going to now have to describe a little bit more about how Parquet is actually stored on disk for this to make sense. But the idea is, the actual way data is stored inside a Parquet file is it's stored in pages. So each column is actually written in chunks that are called, I suppose they're called column chunks, but really each one's made up of a sequence of pages. And so in order to read the data that you want out of a Parquet file, the first thing you need to know is where the pages for the columns you want to read live within the file, so you can fetch them and decode them. And so traditionally, if you don't know anything else, if you just have the file, you got to go fetch. There's a metadata footer at the end. You fetch the metadata footer. It has all the information you need to then go find the relevant pages and decode them. So if you have to do that, that's pretty slow, because you have to not only do you have to do an I/O to get the footer, then you also in the critical query path have to decode it, figure out where the pages are, then go back and fetch the pages and then decode the pages. Right. So that's quite a lot of overhead in your critical query path. People who care about latency almost always, unsurprisingly, if you really care about latency, you would cache that first step, so you don't actually have to go fetch the file footer and parse it as part of the critical query path. You have some pre-processed version of that. Maybe that's an in-memory index, maybe it's in Redis, maybe it's in Postgres, who knows, but it's somewhere else that's much lower latency. So you use that external index, and then you can read those pages directly from the storage, and that's about as, it's not clear how you get much better than this, right? You have control over the external index, you go fetch the pages you need, there's no file format changes needed here. Now, there's definitely a lot of engineering effort required to build these indexes, keep them up to date, make them fast, all that sort of stuff. By the way, you can read all about this I have a whole blog post about this if you want to read it in more depth. So, but my point is, I don't think you need the file format changed if you really care about, the latency parsing metadata does not have to be a part of your critical path on your query path. and that you don't need any change today. Another thing you can do is improve the existing implementations for thrift decoding. Thrift is basically like protobuf in the sense that it's actually pretty space efficient, but in order to parse it, you basically have to walk through all the bytes and find where the fields are. However, that doesn't mean that the existing software is as fast as it possibly could be. This is another example from an Arrow blog I wrote with Ed Seidel earlier last year, I guess 2025, and we basically showed that, well, not just showed, we did. Ed rewrote the thrift parser basically, and it got 3 times faster in the Rust implementation. And we prototyped a little bit more. There's a whole bunch of other things you can do, right? Like thrift was basically designed to be a network message passing format, and so the automatic created decoders will automatically parse the entire structure into in-memory structs and all individual allocations, right? So there's a whole bunch of allocation overhead in addition to the parsing overhead. And if you're only reading a few columns out of the file, there's no reason you should be parsing the metadata for all the columns. But that's pretty much what all the open source readers do today anyway. So with some more careful allocations, you can, I think there's quite a bit more performance you can get, probably another factor of 3, certainly in the Rust one. And, hopefully someone will decide to do this rather than just continue to say how bad thrift is. But I think, so my point is here, there's still a bunch more overhead that you could eliminate with just careful software engineering without having to first change the file format. I do think there's a floor here, however, and that if you want to go faster, you would have to change the format. And in fact, the way people would propose to change the file format is change how the metadata is encoded. Most people seem to like flat buffers. They use that as the alternative, right? That's basically a technology that you can map in directly. We actually there's a proposal I was saying to add something like that to the Parquet spec as well. If you're interested, you could follow the link on the slides. But of course, there's trade-offs with flat buffers. Well, actually, I should say Lance doesn't actually use flat buffers, I found out from Weston, but instead it uses protobuf, but it stores the protobufs for each individual column separately, so that you can quickly go figure out the ones you need and decode just them, not all of them. Which anyway, so of course it's not always better to use flat buffers, despite what some people or the internet might tell you. One challenge is you still have to validate flat buffers if you don't trust it, right? You still basically have to look at all the bytes and make sure that the offsets are within bounds. And the other thing is, because flat buffer is meant to be able to be read directly from memory, it's not particularly space efficient. And so the metadata is actually huge unless you are careful. And so typically, a lot of times you'll like ZSTD compress the flat buffers. So you lose some amount of the benefit by now having to run a general purpose decompressor on it just then to parse the metadata. So I'm not saying it's not better than thrift, but I don't think it's maybe as great as maybe some people think. All right, so that's basically the high level thing. How do you deal with metadata? You could either use the existing system or you can make it better. Now the other thing I want to talk about, the next common gripe is that, and they're kind of related, so I'll talk about them the same because I think they have the same underlying source, which is that the latency of reads and that it's slow to read a particular row, right? Slow random access. And I wanted to point out the actual use case. I'm going to show all these examples for querying a single row, but the actual use case is not just fetch a single row, it's fetch a lot of like individual rows. So it's fetch like, give me 1,000 rows that are sprinkled all over the data set. They're not clustered anywhere. So you just want sort of 1,000 arbitrary rows to feed the RAG model, right, that I showed in that architecture earlier. And so the idea is, if the overhead of fetching a single row is so, it's like 1,000, or if it's massive, fetching 1,000 rows, like it really becomes a bottleneck. This is something I didn't fully appreciate early on when people would complain about single row lookups. I was like, well, if your actual use case is literally looking up a single row, a giant overhead for that row is maybe not that huge a deal, because you're gonna have to wait for the IO anyway. But in this case, when you're really fetching 1,000 rows in the IO, you can batch the IO. I think it becomes a much bigger deal. All right, so the reason it's slow is typically, this is to read, right? Because typically the pages that store all the data for Parquet are both compressed and encoded. So that means first they got run through a general purpose compressor, or first they got encoded using some particular scheme. It's often RLE bit packing, because that's the default. Then it's compressed, and then it's run through a general purpose compressor. So in order to read it, you go through the opposite steps. So in this case, you would have a encoded compressed page. First thing you have to do is decompress it, like with ZSCD or Snappy. That gives you a bunch of bytes that are encoded. The default in Parquet is use what's called RLE bitpacked hybrid. So basically, depending on how many subsequent rows are equal, and basically the writer gets to pick. But so we can either pick to store the row as a bitpacked, a couple of bitpacked rows, or store as RLE, run length encoding. The details of that, you can read all about them in the spec if you want, but the practical implications, if you want like the value down here, you basically have to decode all the rows previously, right? So you have to go through and individually decode all this stuff to find this row. So if all you really wanted was this row, you did a lot of work. You decompressed it the whole page, and then you had to go and scan basically and do the decoding, practically speaking, up until that. So that's where the single row overhead comes from. You can imagine doing that now for every single column, and you're talking real time. So the first obvious thing to do that is actually very common in many systems is, rather than caching this data, like when you read it off disk, you actually cache the decompressed page. So yeah, you have to decompress it once, but then you cache this decompressed thing, and so then subsequent reads don't have to do the decompression step. And this decompression step, like, you do queries, often this decompression step is like 20-30% of the time if it's a really computationally intensive situation, especially if it has strings, for example. So anyway, caching here is a major way people improve this situation today. The other thing you can do is, if you want to go crazy, this is some work I did with Zhengping Hao at the University of Wisconsin-Madison, which is, if you're going to cache the data anyway, and your cache has a bunch of memory and a bunch of CPU, because that's what you have to rent these days from the cloud, what could you do with that CPU? Well, you could spend the time with the CPU actually transcoding the contents of Parquet into something that's more amenable to the computation processing you want to do. So rather than caching like decoded Parquet pages, you could like transcode it, for example, into an encoding that's more efficient for single row access, like Arrow or some of the other more modern encodings we'll talk about. So, you can go read the paper. It's in VLDB this year. I just want to give you at a high level what it does is it pushes predicates down into the cache, and the cache has transcoded the contents of the Parquet files into some form that's much more efficient to evaluate these predicates on, and then sends the results right back to the compute layer. So again, there's a whole paper about this if you want to read it. It's great, but this is another thing you can do. This doesn't require any changes to the Parquet file format. The other thing, of course, you can do today, right, with no changes to the file format, is to use plain encoding. So for integers, it actually works pretty well. If you want, plain encoding basically means don't encode it. It just means like slap the integers one after another in the page. So after if you want really fast random access, you just don't compress it and don't encode it. And so if you want this value, you can just literally read the row directly and you're done. Right? That's pretty efficient. Hard to see how that works better. However, so it is super fast random access. The downside, of course, is that the compression is terrible because you're storing this whole thing uncompressed. You could, you can play around with the I/O sizes if you want, but it's basically basically people don't. If you're going to do this, you might as well store it as Arrow files, which are pretty big. Unfortunately, actually, it also doesn't work for variable length strings. So the way plain encoding works for bytes, so either bytes or strings, unfortunately, is the way it's actually organized so that it has the length followed by the string value, length followed by the string value. And so if you want to decode the Xavier row, what you have to do, you have to walk down and basically skip over all the strings previously and get the Xavier. So even plain encoding for variable length bytes doesn't help you in this. If you really care about, you still have to do quite a lot of work. You don't have to read those strings necessarily, but you definitely have to go walk over the memory to find where it lives. So plain encoding for variable length strings is not really great. There is actually an alternative form of string encoding called delta length byte array, which is unfortunately approximately the same in terms of the overhead for doing single row lookups. It's arguably more efficient space-wise, and you can decode the lengths faster, but you have to. So basically what they do is they store the lengths as a separate header thing in front of the binary values, and then they find the common length or the minimum length, they subtract them all, and they bitpack these. So these are stored very efficiently. They're bitpacked, but it still means if you want to query for that row, you've got to walk through all the encoded lengths, decode them, figure out the actual offset in the file for the bytes you want, and then go read that. So unfortunately, it doesn't really have great random access properties. So that's what Parquet currently supports today. What people have proposed is adding encodings that actually, the ideal is you have encodings that compress similarly to these general purpose compression algorithms, but still maintain the ability to decode individual rows very quickly. So like with random access. So in this case, you can see one is called ALP. We're in the process of discussing this in the Parquet mailing list actually right now. Pratik's been doing a great job driving that forward. But ALP is an algorithm out of the CWI research lab in the Netherlands with Peter Bonse and Azim Afrouz. And basically what it does at a high level is it stores floating point numbers as bit-packed integers, the details of which you can go read the paper about. It's quite clever. But basically what it means is that then if you want to go fetch a particular, decode just that row, you can read its encoded form using these parameters that are stored. You can actually then apply a mathematical transformation and get back the original floating point number. So this is actually an example of, it's very fast. It compresses almost as well as some of these ZSTD compressors for common data sets, but you can also decode it very quickly. There's also similar encodings for strings. So here's an example of FSST, which is one out of TU Munich, I believe. I think it's also Peter Bonse, but Victor Lees and Thomas Neumann as well. It's an encoding that they proposed that also has good compression properties, but still also maintains random row access. So in this case, the way it works, just to give you a flavor, is you have a symbol table. There's a symbol table with a fixed size, typically 255 entries. The 256th one is reserved for exceptions, basically. And then each, obviously the lengths of the symbols, and then the way strings are encoded is there's the offsets to the beginning of the string, and then each string is encoded with a sequence of bytes. But basically, these are symbols in the symbol table. So in this case, if you wanted just that row, you read the encoded form 0194. You go look up 0 means HTTP : / 1 means www, 9 means VLDB, and then 4 means org. So you store these substrings. You can reconstruct the original string and come back here. There's no surprise. There's no accident that this is showing URLs because that's an excellent example where there's lots of repeated substrings, and so this encoding works really well. So not only do you get good compression by this encoding mechanism, but you still maintain the single row decoding ability. So that's pretty cool. So that's another example of encoding that's been proposed and added to being proposed to add to Parquet, and it's commonly used by some of these other file systems. So now, of course, this is being presented to a research group, and so one of the things I wanted to say was, so now if you look sort of more holistically at what the storage cost is, aka how good the compression is, and how fast you have random access speed, and one down in the lower left is the thing that we have today, which is it's very efficient storage, but it's very inefficient at random access speed. So you RLE bit packet and ZSCD it super well compressed, and the other end of the spectrum is kind of plain encoding, no compression, very high storage cost, much better random access speed. People think FSST, ALP are down here, but I don't actually have any idea how this chart actually looks. So it would be awesome if someone wants to actually go through and figure this, where these points are on the chart, because I think that would actually really help. Like, is this here? Is it over here? Right? Is it, is plain encoding really terrible? I don't know. And so we can sort of hand wave, but having actual data would be amazing. All right, the next thing I want to talk about is, I'm going to switch topics, and I would talk about people's complaint that Parquet is very slow or memory intensive for storing large binary things today, or large strings today. And the first thing I think you could do is just improve users, and I will show this by an anecdote. So I went a couple of days ago to Hugging Face and just picked whatever the most, the current trending data set was. It happened to be, it was presented as Parquet files that were stored as images. So I downloaded one of them, and I used Xingping's great Parquet viewer to look at it, which lets you see the structure of a Parquet file. And I'll just point out some things here. So this data set has some sort of images, and then machine learning prompts and results or something. I don't really know what the data set is. I just picked it because it was trending. It was created by Parquet CVP Arrow version. Well, this is almost certainly Pi Arrow, right? This was created by, and it's from July, so it's this past year. So it's basically a recent version of Pi Arrow. But if you look at how is the binary actually encoded here, right? Here's the image. The image is actually stored as a struct with the binary bytes, and then another column with the path stored as a struct. It turns out that the way it's stored is really not good. It's stored as, it's like RLE encoded and dictionary encoded, right? But since these are basically JPEG images, RLE and dictionary encoding are entire overheads. They're all unique binary bytes, and there's no repetition in the set. So using this encoding is entire overhead. And then likewise, because they're JPEG encoded, they don't compress basically with Snappy at all, and so Snappy encoding also doesn't cause their compression. So basically, RLE, this encoding and this compression are entire, like basically only overhead. They don't reduce the compression at all, and they don't increase the compression level at all, and they decrease the speed at which you can read the bytes out of this file. And yet here it is on one of the most widely used data sets. These people should know better probably. And I'm not trying to say anything bad about Hugging Face. I'm just saying, by the way, these are the default settings of the Parquet writer in C++. That's where these come from. So this is an example of like, yeah, this Parquet file is going to be pretty bad to read out as, read the binary bytes out, but without changing the format at all, it could be so much better by just adjusting these parameters. Right? Maybe we need to work on making the writers better or more efficient, or teaching people or something, but you don't need a format change to get a significant win here. The other thing I wanted to talk about was that often comes up when people talk about reading large columns out of Parquet is the amount of memory required. And they'll often talk about Parquet requires buffering data at the row group level. And in my opinion, so what that means is like when you're reading some number of columns out of Parquet, there's like it gets broken down in these horizontal strips, these pack strips like I talked about. And then when readers go to read it, they'll figure out which columns they're going to read, figure out which pages are relevant, and then they basically read all the relevant pages from those columns into RAM, and then they incrementally decode and decompress each page as the engine needs them. Right? So this is basically how all open source readers work that I know of. And the downside there is, of course, that these have giant string columns in them, and you fetch a whole bunch of giant string pages, it's going to require a lot of memory. But now, it's even worse if you're also caching uncompressed pages, right? Because now you're uncompressing giant strings. But there's absolutely no reason why you can't just read one page into RAM, decode it, and then go get the next page, decode that, decompress it. You don't have to change the file format for that. And this is much more sort of memory efficient, although you do have to decompress the page. But of course, I think the reason why a lot of the open source readers are implemented the way they are and they buffer at the row group level is because that tends to have a reasonable trade-off between reducing the number of individual IOs, so not having IO stalls, but also not having to buffer the whole thing in RAM, the whole file in RAM. So basically, this is, if you care about reducing the memory usage of Parquet readers when reading large string columns, I think there's a lot of software engineering that could be done that would improve the situation dramatically without having to change the format. All right. The other thing, of course, you can do for memory-intensive large strings is get better encodings, right, that don't require having to decompress the whole entire page in order to read a single string value. I already told you about one of them called FSST. I'll bet there's a lot of other clever researchers that hopefully are listening to this talk or hear about it. I think this is another very interesting topic of research for the AI workload, right? Can you come up with string encodings, binary encodings that work, they're efficient to compress but don't require decompressing the entire block in order to read one value. And the final thing I want to talk about is taking advantage of SIMDs and GPUs. There is in fact a specialized Parquet implementation for GPUs today that's part of the CUDF project from NVIDIA. So you might ask, well, they've already figured out how to read Parquet with GPUs. What's going on, Andrew? I think anecdotally, it's not clear to me that this reader is fully able to take advantage of the GPU, and I don't think it's because of the lack of engineering from NVIDIA. I think it's something fundamental about those encodings, like specifically that you have to decode the previous value in order to get the next one, and so that fundamentally limits the parallelism that you're able to get out of your GPU, because you can't run 20,000 decoding threads in parallel. You have to decode the stuff one after another. So maybe you can run one thread per page, but that's it. Also, some other anecdotal evidence is that I was talking to Will the other day, and he said, according to his measurements, again, take this as a grain of salt, I haven't verified this, but that he could get 91 gigabytes a second using the CDF Parquet reader, but if he used his fancy new Vortex reader, it went something like 5,700 gigabytes per second. Again, I don't know if those numbers, I haven't verified those numbers, but I think the idea is that there's an awful lot more processing available on the GPU than the current Parquet implementation can really take advantage of, and I think it's fundamental about the encodings. And in fact, so what are we going to do about that? The obvious thing to do is to introduce encodings that are more amenable to GPU processing. So I think traditionally, I would imagine mostly what that means is that they don't have data dependencies. So in this case, ALP sounds like it's actually pretty good as I presented it before, right? You just, as I presented it earlier in the talk, you just go read the value that you care about and you're done. You just apply some math. So that should be crazy parallelizable with GPUs. You just let all the GPUs do that in parallel. They don't have to think, they don't have to look at anything, whatever. However, something I didn't mention that's part of ALP is it's very important to ensure that the data is losslessly preserved. And so the transformation I described, you might lose precision on, if your floating point number has a particularly large range or something, or there's one value that's wildly different or something. So the way ALP handles that is it stores an exception table. So if you can't losslessly encode the values, instead what happens is they get stored in their full form. It's like in a prefix in a header page or something. So practically speaking, what that means is when you want to go decode a particular row, what you first need to do is look in there's like a list of exceptions that you have to binary search. And if you find that the row you care about, exception index is actually in the exception index, you then have to read the corresponding entry out of the exceptions value. So now this is a whole bunch this is some non-trivial control flow now that gets inserted into each one of the decoding of each one of these things. And I think if you're not careful, you have the GPUs, going nuts on here and causing all sorts of memory bottlenecks, because now they all have to share this decode page. The ALP people are definitely not surprised by this. They have another paper that describes how to potentially, one way to make this more amenable to GPU encoding, but it already has some trade-offs. Like in particular, it's actually less space efficient. There's additional overhead, and in my opinion, this is still an area that needs some more work on like how really to design an encoding that would best take advantage of GPUs that you can still efficiently implement on CPUs and doesn't have a giant, storage overhead. So, with the last few minutes, where are we heading? Basically, we have two options from what I can see, right? Two ends of the spectrum. The first is we're going to have some single format Parquet that can serve everything. Basically, we'll extend Parquet so it's good enough at low latency reads, random reads, take advantage of GPUs, that kind of stuff. And we somehow convince people to invest more time improving the existing readers and writers to, not be to be better in the cases that are becoming more important, like wide schemas, for example. So I mean, this is one view of the world. By the way, they can both coexist. Another option is that a new file format emerges that gets adopted widely for AI-centric workloads. And maybe that would result in, maybe it's okay to have two file formats if you have two wildly different use cases. We'll see, but that would, it's not as theoretically pleasing as a single format. So, what's my prediction? I think we're going to find out in the next year or two what's going to happen. Julien, of course, says he thinks it's going to take longer than 2 years, but that's why it's fun to make these presentations. I don't actually have to be accountable for my predictions, probably, although it's on YouTube. We'll see how long it goes. So over the next 2 years is going to be an interesting thing to see. The final piece of actual information I have in this slide deck is a comparison by format for some of these file slides. Thank you very much to Will and Weston, Andy, and Zinu for their help making sure I didn't mischaracterize these things. But this is like my attempt to list some important features of the file formats and then show what features they all have. So this is the slide that shows where they're mostly similar. They basically all have columnar layouts. They all have some sort of Apache Arrow compatible type system. They all store data in these like pages that are chunked basically according to the pack scheme. So you chunk each column into little pieces rather than write the whole thing at once. And depending on how you define row groups, many of them have row groups. You could like Vortex might have row groups. Lance, maybe has stripes. It's turned out when people talk about what row groups are, there's at least 3 different things they're talking about. They're talking about IO clustering. They're talking about metadata for some unit that's not the page and it's not the file, but somewhere in between. And they might also be talking about the unit of like the prefetching that the reader does, or some combination of the 3. So anyway, the fact that these are X's, I don't take that as too big of a thing. I definitely have an agenda here too. If you look at the slide, they're all, they're all pretty similar, right? They all basically have greens in there. Then there's the metadata parsing. Parquet, like I said, has a spec outstanding a proposal to add flat buffers to improve the metadata processing performance. All these other systems either use flat buffers, that's what these 3s are, or in Lance's case, it uses protobuf, which is similar to Thrift, but they split it up individually per column, so you can easily go find the metadata for the column you care about and not have to parse through the whole thing. And then here's where it possibly gets more exciting, although even this slide has a whole bunch of green. Basically, all of the industrial file formats support general purpose compression. The academic ones don't. I think this is probably a reflection that in the real world you need some sort of general purpose compressor to fall back to for certain data sets that you don't have good encodings for. So I think it's just like an engineering reality that you need that in the file format, even though you would ideally not use it for high performance. They all basically have the classic RLE bit packing algorithms, the sort of standard encodings from the column store research from 20 years ago. Where I think some of the differences start to appear is the random access from the encoding. So I've talked a lot about ALP and FSST. There's also a related paper called Fastlane's bit packing. It's still bit packing in the sense, but it's explicitly designed to really be much more parallel than a lot of existing bit packing algorithms. And it still retains the single row decoding. Parquet doesn't have that yet, but it has proposals for both FST and ALP, and actually ALP is quite far along from what I can tell. Lance also includes FSST and Fastlanes. Vortex includes all 3. Nimble doesn't appear to, although I couldn't swear to it. I'm not as familiar with that format. Both F3 and Fastlanes also have all 3 of them. Interestingly, all of the formats have some version of cascaded encodings. So a classic example is dictionary encoding, where we will take the data and you'll remove repeated values and replace it with an index into a dictionary, and then you actually encode the dictionary separately. So that's a cascade in the sense that the dictionary is encoded. You first dictionary encode the data, and then you encode the dictionary again. So Parquet has that; it's had it since the first version. As to all these other file formats, it seems to be very important. Many of the newer file formats, actually basically all of them except Parquet, allow you to do sort of more explicit cascadable encodings. So like Parquet basically has a few hard-coded, like dictionary specifically. I think that actually might be the only one. Or you could argue that Delta Binary Pact also is a cascaded encoding, but it's basically hard-coded what the cascade was. A lot of these other file formats allow the different cascades to be selected based on the particular data type, so there's a lot more options of what cascades are available. And then another interesting feature that's shown up in a couple of the papers is extensible encodings, either via WASM or maybe something else. So that's if you don't, in order to avoid having new encodings, having to go through the effort to change the spec, you could plausibly add the encodings as a WASM file, either as a reference or directly in the file, so that you could take advantage of new encodings without having to change the file format. Since that's not widely, that one's a little farther off, I think. But otherwise, these look pretty similar, right? There's a lot of green there. And again, I have a bias, right? Like, I'm a freaking PMC member of Parquet, right? I think this column's important, and from my perspective, it's not that far away from what these other ones are doing. The biggest missing gaps are these random access friendly encodings, and we're actively working on that. All right, so to conclude, I think you're going to see Parquet become significantly more parallelizable in the next 12 months, basically by adding new encodings. I also think you're going to see the industrial file formats of Vortex and Lance basically put into production by startups, and we're going to get a bunch of real-world production experience. And in my mind, this GPU optimized encoding stuff is still very much an open question. Maybe I just haven't caught up on the research enough, but I think this would be a place where I think there's a lot of interesting work to be done. So basically, what I expect to happen over the next 12 to 24 months is that we're going to have a horse race where the Vortex and Lance people who have a lead on Parquet technologically right now are going to have that amount of time to try to extend their lead, and Parquet is going to catch up, much more slowly than because it has to bring a whole community along with it. But we'll see where it ends up. It's going to be interesting. I think it's good for basically everyone involved. And so with that, thank you very much. As I have to mention and end all these talks, I always encourage everyone to come help join us, right? Like I was talking about engineering effort to make the Parquet readers better, right? Like all that stuff's open source. You can help. It's not easy. It takes time. Maybe it never goes quite as fast as you might want, but we're always looking for help. And so please, we'd love to have you. There's a bunch of links here if you're interested. So anyway, with that, thank you very much for listening, and I hope to see you online. Feel free to drop me a comment or note or whatever if you have any questions. Thanks.